We're moving from inference for proportions to inference for means. And the good news is that maybe 80-85% of what we did before, at least the structure of what we did before, applies to this too. In fact, it's going to apply to all the things we cover pretty much the rest of the way for the year. So if you feel that you have good mastery over the material we just tested over, then you should be able to pick this up no problem at all. So starting with this, if you think back to chapter 17 when we introduced sampling distributions, we had a standard error for means of sigma over square root of n. And the problem with that is that realistically, there's no way we would ever know sigma. It's a population parameter. Parameters are things we're just not supposed to know. And that's going to be a problem if we need it for inference. So since we'll not know that value, we're going to replace sigma in that formula for standard error with standard deviation from a sample, which is S, or S sub x. And it's going to be, in place of sigma, it's going to be an estimate for it. Now, the issue that we were going to run into is that sigma is a fixed number. It is the standard deviation for the population, right? There's just one of them. Whereas standard deviation from a sample, well, it kind of depends on the sample you pick. So every sample that you can grab of a certain size from a given population will probably have a slightly different standard deviation, right? So that's going to create a complication for us. And the way we're going to resolve it is we're going to use a t-distribution to do our inference instead of a z-curve. All right? And there's a reason for it. And let's just go ahead and examine that. First of all, don't be overwhelmed. T-distributions and z-curves are pretty much very, very similar. And there are many t-distributions. So every sample size you have has its own t-distribution, right? And another way to address sample size in statistics is to go to degrees of freedom. You calculate degrees of freedom is n minus 1. So if you have a sample of size 25 and you want to know the degrees of freedom that you have, just subtract 1 and your degrees of freedom comes to 24. So that's very, very simple. Now, the higher the degrees of freedom, or another way to say that, the bigger your sample size, the closer your t-curve gets to becoming a z-curve. And when we look at that z-star table that we've been working on, you remember all those numbers above the z-star values? And we're like, what are they for? There's like billions of them. Okay, I exaggerate, but there were a lot. And well, those numbers all come from t-distributions. So we're going to get to that. But the higher that your degrees of freedom or your sample size is, the t-curve is going to approach a z-curve. So a t-curve with infinite degrees of freedom is a z-curve. Okay? So you're already gaining the sense of perhaps these things have a lot in common. And they do. All right, so the black thick curve, the line that makes up this curve, the thick black one, is a z-curve, right? And the other two, the blue and the red, are t-curves. All right. The blue one has 6 degrees of freedom, so it's made up of all possible samples of size 7. And the red one is 2 degrees of freedom. It comes from all possible samples of size 3. So let's see where they're the same. They center at 0. All right. They're also bell-shaped, all of them, right? And you measure discrepancies away from 0 with standard deviation units, whether it's a z-curve or a t-curve. What makes them different is, remember that extra variation you have to deal with when you use S in your standard error instead of sigma? Well, that standard error all goes into the tails. That's the extra variability that you're looking at. And since all of these curves are density curves, if you have more area in the tails, then the peak has to drop down. And that's the same for the blue, right? So it's going to be very, very similar, but we're going to have t intervals, and we're going to have we're going to get t statistics and do t tests. all right, because we're in T curves. All right, so just what I said, density curves for T's are similar in shape, they're bell-shaped, and the spread of your T curve is a little bigger than your standard normal curve because of the extra variance you get from using S in place of sigma. All right, so you need this. Since we won't know sigma, our standard error will be S over square root of n, not sigma over square root of n, all right? All right, another thing that's really good for t-tests and t-procedures is that they are robust. And robust means that they can just handle things well that perhaps other procedures can't. So if violations of assumptions do not greatly affect outcomes of inference, a test is called robust. Specifically, t-procedures are robust against non-normality of the population where there are no outliers. All right, and we'll go over some guidelines in a minute. But t-procedures are very badly affected by outliers. If you have an outlier that you can identify in a small sample, and we will be dealing with samples like 8, 10, 15, things like that. If you have an outlier among those values, then you don't have symmetry. Sorry, you're not symmetric. You're not bell-shaped, mound-shaped, any shape, except skewed, because an outlier is really part of a skew. So that's really kind of how bad a skew can get, so we aren't going to do t-procedures with outliers. I mean, we can do them, but we're going to have to mention that we worked through them and that they're a problem. Okay, so here's these three. If your sample size is below 15, then you got to be serious about your normality checks. Look for outliers. Anything that's kind of badly skewed, it's a problem. Anything from 15 up through 30, you can relax a little bit, but outliers are still a problem, and strong skewedness can also be an issue, so look for that. Of course, we're talking about raw data, graphing raw data. If you're at 30 or higher, don't worry about graphing. Or maybe you're just told that your sample size is 50 or something like that. That means that you're good to go. You don't have to worry about outliers. You don't have to worry about the shape of your population. That is the central limit theorem. Remember that? That's what we learned in chapter 17. Now it says here to use a normal probability plot to check for normality. That's fine. But if you're going to check for outliers, this plot won't show it. So do a box plot in your calculator because it instantly shows you outliers. If they're a problem, we need to know it. And that's another thing. I get some people that opt out of checking for outliers, and on a test or a quiz, you can bet your bottom dollar I'm going to slip a couple in there, and you better find them, right? Because if you don't, then I will catch you at not finding them, and it'll be I won't say a substantial penalty, but you won't like it. Okay, so let me put these all up here. Whoops, went past it. Okay, I've got a story to tell. SRS and independence. Okay, so when I was at my textbook adoption meeting, I was with two other teachers in the district that do grading for College Board. And they mentioned that every time you do a set of assumptions or conditions, you need to say independent. Even if it's one sample. Now the two sample, we did do that for proportions. Because we don't want anybody being in both groups, But now, apparently, and it includes proportions too, we have to say independent for one sample. The thinking is that you're just saying that no one person was measured twice, like for height. You didn't get two measurements for height from one person. To me, that's pretty picky, but it is what it is. And they grade on that. And it's coming right from graders. So I want you to put that on everything except one test that we're going to do next week. And I'll highlight that. But apparently it's something that needed, and I didn't tell you before our proportions test, our chapter 17 through 21 test, because I didn't want to throw out a change at the last minute. But now that we can back away a little bit and take a breath, let's just use independence along with SRS in just about everything. All right, there's your 10 times, or condition, population 10 times the sample size. All right, so normality. If they tell you the population is normal, you're good to go. All right, then your sampling distributions are normal too. If you have raw data, especially if it's below 30, graph, and no histograms. No histograms. Let's just do modified box plots, which they come out that way, or normal probability plots. Just switching back and forth is pretty easy. Check for outliers. Don't forget. If you're at 30 or more, you're going to approximate by central limit theorem by your sample size. So that's good. And if you have no other way to move forward, nothing that you can claim for normality of your sampling distribution, then just assume it. And if you feel like you need to list it as a limitation at the end, that's fine. Okay, and these guys are the kind of the underpinnings for your confidence interval, sample estimate plus or minus critical value, which in this case is a t star, times your standard error, s over square root of n. So standard error, margin of error, and confidence interval. All right, one sample t-test. This is like a z-test, but it's not, all right? It's your sample estimate minus what you have in HO divided by your standard error. And that's kind of the way a test statistic works. And this is the way a confidence interval works, okay? All right, that's the homework. So I'm going to move into the notes that we did in the packet, and I am not going to write them in front of you. I am going to just post them up here and work on the calculator with you. And let's see, that's something else. Okay, so here are the notes, and this is on page 4. And when you get to a point where you need to write and not listen to me move away from what you're doing, then just pause. All right. So, so Nabisco announced a 1,000-chip challenge, claiming that every 18-ounce bag of their Chips Ahoy cookies contained at least 1,000 chocolate chips. Okay. So stats students purchased some randomly selected bags of cookies and counted the chocolate chips. So there's 2, 4, 6, 8, 10, 12, 14, 16 data points. So n is 16. That makes for 15 degrees of freedom. Okay. So we'll start out by defining mu. All right. Before it was defining p, but now it's mu. Mu is the true average number of chips in an 18-ounce bag of Chips Ahoy cookies. Okay. Yeah. So there's that. And then assumptions. They said that these were randomly selected. See the randomly? All right, so that's a good thing. SRS and independent. But there's way more than 18 bags of Chips Ahoy cookies out there, so population is at least 10 times the sample size. And we got to check normality. Well, we have this data, so I conveniently put the data in the calculator, all right? So why don't you take a moment to get your calculator out and load these 16 numbers in and put an X up here. So pause. All right, I'm going to assume that you're back. And so here these things are. And we're supposed to do a normality check. Well, we're below 30, so no central limit theorem this time. So let's go ahead and do menu. And, oh wait, we don't want that yet. What we want to do is go home and then scoot from your spreadsheet one to the right, and that's your stats graph, so go ahead and pick that. And hopefully you named your variable. I named mine X. And so there's all my data collapsed down like a dot plot. So I'm going to convert that into a box plot. All right, so menu, plot type, and box plot. All right, number 1, no outliers. That's good. Number 2, reasonably symmetric. Yes, there is a skew to the right. Let's not get picky about it. Remember, T procedures are robust to that kind of thing. So this is remarkably symmetric for a data set. Let's go with it. And let's go ahead and convert that to a normal probability plot. All right, so there it is, choice 4. Okay, now you may not remember this too well, but if this thing lines up really well to a straight line, slanted albeit, but if it lines up to a straight line, then your data fits a normal model well. Now you can get bendies. Like if this is a big bendy like a chair, then it really doesn't fit a normal model too well, but it's lining up good for sample data. So this is what I wrote. Let me get this back up here. I said box plot is reasonably symmetric without outliers, so the sampling distribution is approximately normal. Right? You could say sampling distribution is approximately normal, or the normality of the sampling distribution is verified graphically. Something like that, okay? Okay, so the next thing is create a 95% confidence interval by hand. Now we're not going to do this as a rule, but we're doing it now. So just to give you the underpinnings, and remember that it's x bar plus or minus t star times s over square root of n. So we need x bar and we need s, and we also need t star, okay? Now one thing I didn't do on here is to name this interval, which I did during class, but you should say results for a one sample t interval for means. Now that sounds like it's a little bit too specific, but keep in mind that there is such a thing as a two sample confidence interval for means, all right? So we don't want to confuse people into which one we're doing. Also, you want to say it's a t interval for means because you can do t intervals for other things like that aren't means. So be real specific when you name it. All right, so where did these two numbers come from? X bar and s. All right, so let's go back to the calculator and let's go home. All right, we're still in that same assortment of pages for the same problem. Let's go to a calculator page and hit enter. And let's go ahead and do a one var stats. So this is menu, statistics, stat calc, one variable stats. It's number 1. And we only had one list, so go down and, oops. Let's see. Come on, hit OK. Okay, I named my X list X. Handy. Frequency of 1, keep it, leave the category, 2 category fields blank, go to OK. All right, there is, oops, it's up here somewhere, there is X bar right there, and there's your standard deviation of X right there. It's not the thing above it, it's just that one right there. That's where I got it. You don't want sigma sub X. That's the only time we use that was for random variables, so we don't use that. And that's really all we need. That's just those two things. So that's where those two come from. Now we again have 15 degrees of freedom. So we need a t star number. All right, so here is the t table. It's in the back of your packet. And you remember that if you went down here to get your z star numbers, you found the confidence level you wanted, and you just read up, and there it was. That's for a z interval for proportions. But what we want is a t value because we have 15 degrees of freedom right there. So just read across and straight up from 95%, and your t star number is 2.131. It's a little bit larger because of the extra variation that you see when you're dealing with, using s instead of sigma. So that's where I got this. Actually, 2.131 is fine. I got the extra ones because I did it a little farther out on a calculator, but 2.131 is great. All right, so there it is, x bar plus or minus t star times s over square root of n, and you get this. Don't forget to name it right. And then you just give the usual thing. We're 95% confident that the true average number of chips in an 18-ounce bag of Chips Ahoy cookies falls in the interval from here to here. And I really should have put chips on there because you can put units on this. You know, it's the average for things that really exist, so they can take units. Okay? So there it is. Now, I would not want to do this by hand, but I'll show you what it's like on the calculator. So coming back here, we can come down to where we left off, like right in here. And we're just going to do menu and statistics and confidence intervals. And you see the T interval right there, number 2? All right. So we're going to input data because we put data in a spreadsheet. So we're going to hit OK. And remember, our X list is X. So that's good. Leave that frequency at 1. That's the right confidence level. Hit OK. And there are the 2 numbers that we had. That one and that one. There's your X bar. There's your margin of error. Everything is there that you can want, including your degrees of freedom. Very nice. So that confirms what we got up here. All right. So the last thing here is, what does your evidence say about Nabisco's claim? Remember, they claimed that there are at least 1,000 chocolate chips in their bags of chocolate chip cookies. So use your confidence interval to test an appropriate hypothesis. All right. So I made a hypothesis. HO is that mu is 1,000 chips. All right, that matches up to what they said. It's the lowest value that they can get and still support their claim. HA is where you're thinking, oh, maybe they're lying. That's less than 1,000 chips. All right. So if you look up here at this interval, do you see how 1,000 is way, way before the lowest value here? And they wanted at least 1,000. Both numbers are clearly over 1,000. Well, since 1,000 is below the lowest number in the interval, there is evidence that Nabisco includes more than 1,000 chocolate chips in every 18-ounce bag. We would fail to reject HO. Make sense? Okay. So if you want, you can pause this and fill in the notes and whatnot. And I'm just going to move on to the second of these. All right, so this is on page 5, I think, and now we're not dealing with actual raw data. They're just giving us summary numbers. So they've got a company, they want to keep their gasoline costs down, so they set a goal of 27 miles per gallon for their fleet. All right, anything bigger would be great, but that's the lowest acceptable amount for their goal. So to check the gasoline usage, they record the mileage of 50 company trips chosen at random. Okay, that's good. 50 is over 30, and random, that's good too. All right, so they found a mean of 2502 miles per gallon and a standard deviation of 4.83 miles per gallon. That seems lower than this. That's not good. All right, it might be only different by sample variation, but it might be that they're not making their goal. Okay, so is this strong evidence that they, that should be a T, have failed to attain their fuel economy goal? So we're going to do a 1 sample t-test for means to get some evidence. So here we go. Mu is the true average miles per gallon for this company's fleet of cars. It's pretty much what it is. HO is equal what they want, 27 miles per gallon. That means they've attained their goal. Anything below that, and they haven't. So you see how this splits right at 27? All right, SRS and independent. We can assume the independence. SRS was pretty much given. I'm thinking they can do way more than 50 trips in their fleet of cars. So the population is at least 10 times the sample size. And N is greater than or equal to 30. It's 50. So the sampling distribution is approximately normal. Sweet, we're good to go. So name it. It's a result for a 1 sample t-test for means. All right, that's really the minimum. All right, 50, N is 50, so 49 degrees of freedom. And we're going to set up our T value, our critical value, or our test statistics, not a critical value. Test statistic, it's X bar, 25.02, minus our HO value, 27, divided by S, 4.83, over square root of N, square root of 50, and you get negative 2.8987. All right, that is saying your sample result is almost 3 standard deviations below the mean in a t-curve. It's okay. You just interpret it just like a z-curve. So if you put this in a curve, it's way out in the tail. And it's looking like we may get a small p-value. But that's all that's necessary. This should be the letter P. Looks bad. Sorry. So at this point in a z calculation, we would do a normal CDF. But we can't because we're in a t-curve. So we're going to do a t-CDF, which is in your calculator. It's from negative infinity up to this number, and you have to add in the degrees of freedom. So let me show you how to get that. And you can stay in this particular screen. So menu, and remember normal CDF in them, they're under probability and distributions, right? And there it is, not only t-CDF, but inverse t as well. So t-CDF, let's pick it. All right, this is already at negative infinity. So I'm just going to keep it there. And I believe this was negative 2.8987. That was our test statistic. And we had 49 degrees of freedom. So hit OK. All right, that's our p-value right there. It's pretty small. So there it is. And it's smaller than 0.05. It's smaller than 0.01. It's smaller than 0.005. So it's really tiny. All right, since p is low, remember p is low, reject HO? So since p is low, the results are significant and we reject HO, there is sufficient evidence to believe that the company has failed to meet their fuel economy goal. Now you can argue like, okay, there's sufficient evidence that the true average miles per gallon of this company's fleet is below 27 miles per gallon. But I like the way I answered it because any reader can understand what's going on. And I answered the question. You know, did they make the goal? Doesn't look like it. All right. So this is not really, I mean, I suppose it could be sampling variation, but it's highly unlikely. All right. So there's your conclusion. But we don't want to do all this mess up here. I don't. So let's just do the t-test on your calculator. All right. So let's get this bad boy up, and we can do it here. So let's go ahead and do menu, statistics, and stat tests. And choice 2 is a t-test. Okay? So the method that we're putting in now is stats. We don't have data in a spreadsheet. So right arrow and down to stats and hit enter. And tab to OK. All right, mu naught was 27, wasn't it? That's your HO value. And get out of there. Your sample average was 25.02 miles per gallon. So that goes there. Your standard deviation was 4.83 miles per gallon. And N was 50. You need that so that you can get the correct degrees of freedom. Now, if you put 49 in there by mistake, you're probably going to get an answer that's so close it won't matter much. All right, come here. Now, your alternate was less than. So you got to change it. If you don't, bad things might happen. Tab to OK. All right, you need 3 things. You need your t value, you need your p value, and you need your degrees of freedom. So that's why I wrote them there where I wrote them, right? T is this, P is this, degrees of freedom is this. You can put alpha there if you've picked one, and it matches to what we had up here. See, same P value. So that's what we covered. I think that you should be good to go. Now tonight's homework is worksheet number 1. I think there's 6 problems. They would be done formally, just like we did here, but make sure on number 5, the one with the persisters, don't do any formal procedures there. There's like sub-questions there for confidence intervals, like comparing widths and things like that. There's enough for you to write without having to write for number 5. The other ones you do, 1 through 4 and 6, but not number 5, okay? Just get your intervals the quick way and do whatever the question asks you to do with them. Okay, so that's it.